Let's continue with some more definitions and notation. The Cartesian product, A cross B, is the set of all ordered pairs where the first item comes from the first set and the second item comes from the second set. So when you see A cross B, it will be the set of ordered pairs such that A is an element of the set A and B is an element of the set B. So the Cartesian product that you are most familiar with is R cross R, so the real number line cross the real number line. That gives us the set of ordered pairs such that A is a real number and B is a real number. And that Cartesian product gives us the Cartesian plane, so the coordinate grid that you're used to plotting points on. So things like -1, 1, 2, 3, those ordered pairs would be elements in R cross R. We can also have ordered triples, ordered quadruples, and so on. So we can take the Cartesian product of as many sets as we like. That just means that the elements will look like A1, A2, all the way through A sub n, where each of these indices, A sub I, is in the set A sub I. We say two ordered pairs are equal if and only if their corresponding components are equal. So to say the ordered pair AB is equal to the ordered pair CD, that's logically equivalent to saying A is equal to C and B is equal to D. The power set, P of S, of the set S is the set of all subsets of S. So in notation, that would be the power set is equal to the set of sets X such that X is a subset of S. So recall the empty set is always a subset of any set. That means the empty set is always a member of the power set of S. In symbols, we say the empty set is an element of the power set for all sets S. Let's look at an example. So let A be the set containing 1, 2, 3, 4, 5, and B be the set containing 4, 5, 6, 7, 8. And let's let the universal set be all of the natural numbers 1 through 10. Let's try and find A union B, A intersect B, B complement, A intersect B cross A, and the power set of A intersect B. So I encourage you to pause here and try and write these elements down on your own, and then unpause the video once you've done that and you can check your answers against mine. Okay, so A union B. Recall that's all of the elements in A or in B, but you don't want to repeat anything. So we'll take the elements in A first. 1, 2, 3, 4, 5. Then I look at the elements in B. I've already written down the number 4 and the number 5, but I also need to include 6, 7, and 8 in the union. So A union B is 1, 2, 3, 4, 5, 6, 7, 8. The intersection contains all of the elements that are in both A and B. So we look at the overlap. A contains the elements 4 and 5. B contains the elements 4 and 5. So the intersection will be the set containing 4 and 5. B complement contains all of the numbers in the universal set that are not in B. So we have 1, 2, 3 not in B, but then 4, 5, 6, 7, and 8 are, so we'll skip those. And then 9 and 10 we need to include because those are elements in the universal set that are not in B. So B complement contains 1, 2, 3, 9, and 10. Now, if we want to take the Cartesian product of A intersect B cross A, so A intersect B is the set containing 4 and 5. We want to take the product of that set with set A, so 1, 2, 3, 4, 5. Elements in a Cartesian product are ordered pairs. The first entry in the ordered pair will come from A intersect B, and the second entry will come from the set A. So let's do all the ordered pairs with 4 in the first entry first. So we'll get this ordered pairs 4, 1, 4, 2, 4, 3, 4, 4, and 4, 5. And then we repeat that with the number 5 as the first coordinate. 5, 1, 5, 2, 5, 3, 5, 4, and 5, 5. So there are 10 ordered pairs in this Cartesian product. The power set of A intersect B is the same thing as saying the power set of the set containing 4 and 5. We want to take all of the subsets of this set. So I always like to start with the empty set because the empty set is always a subset. And then I kind of work my way up. So I've done the empty set, the set containing nothing. Then I take the sets containing one element. So I could have the set containing 4 or the set containing 5. Both of those are subsets of 4, 5. And then I take the subsets containing 2 elements, and that would be the whole thing, the set containing 4 and 5. If you had a larger set, I would build it up from there. Take the empty set, the sets containing 1 element, the sets containing 2 elements, all the way up until you have the entire set, and you would have a complete power set, the set of all subsets. So important to note here, the Cartesian product is a set of ordered pairs, and the power set is a set of sets. So mostly sets contain elements, just like 1, 2, 3, 4, 5, but when we build these new sets, they can have elements that look a little different than numbers. So the Cartesian product has ordered pairs as its elements, and the power set has sets as its elements. Since there is a direct relationship between logic and set theory, we can write down many facts about sets using what we know from our study of logic. So recall the addition rule. The addition rule says, if we have P, then we have P or Q. So if we know P is true, then P or Q will also always be true. This addition rule from logic allows us to prove the following identity in set theory. A is a subset of A union B. So recall this implication symbol is analogous to the idea of a subset in set theory, and the or symbol is analogous to the union symbol in set theory. So the addition rule allows us to take A is always a subset of A union B. We also have De Morgan's laws for sets. So the complement of A union B is equal to A complement intersect B complement. And similarly, the complement of A intersect B is equal to A complement union B complement. Sets that contain a finite number of elements are called finite sets. And we call the number of elements in a set S the order of set S. And it is denoted with these they look like absolute value bars, but they're vertical bars around the set S. So when you see that, we're not talking absolute value because this is a set, not a number. In set theory, this notation means the order of S, and it would represent the number of elements. So for example, if A is the set containing 1, 2, 3, 4, 5, then the order of set A is 5 because there are 5 elements in A. The inclusion-exclusion principle. The order or the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection. I encourage you to draw some Venn diagrams to try and understand the inclusion-exclusion principle better. Try shading the diagram for the A union B, and then shade a diagram for A and for B, and try to understand why we need to subtract off the intersection. And we can talk about this more when I see you in class.